Welcome to this BRSL webinar, Modeling Hypersonic Missile Flight. Thanks everyone for joining us. As a reminder, you'll be able to find this webinar on our website and on our YouTube channel later this week, and I'll send out a note to everyone that was registered as well with that link when it's available. If you have questions during the webinar, you can put them in the chat box, the Q&A box that is at the bottom of your screen, and we'll get started. This webinar is going to be led by BRSL Senior Research Scholar, Dr. Cameron Tracy. His research focuses on the technologies underlying missile systems, missile defense, and nuclear material production. We also have on today's panel David Wright, who is a research affiliate in the Laboratory for Nuclear Security Policy, or Nuclear Security and Policy at MIT. And Justin Lee, who is a graduate student in artificial intelligence at Santa Clara University. Today we'll be discussing the importance of technical analysis in global security studies. And with that, I'll introduce Cameron and toss it over to you.
Thanks, Vivian. Thanks for everyone who made it. Thanks for David and Justin for joining us. So the way this is going to work is I'll start off with a few short slides talking about the motivations for this new tool that we've developed to try and ease the process of simulation and calculation of the performance and security implications of this emerging class of missile technologies, hypersonic boost glide vehicles. After that, I'll hand over to David and Justin. I'll pose some broad questions to them about Justin's work on the development of this tool, David's long-term work facilitating and fostering this kind of technical analysis of global security relevant issues, and then we'll end with some time for Q&A from the audience. So to start with, let me pull up some slides. So, modeling the performance of hypersonic glide missiles. Now, to start very broadly, missile technologies, as we're interested in them, are airborne vehicles that exist to deliver explosive warheads from point A to point B, with those points separated by some appreciable distance, which might be hundreds of kilometers, might be thousands of kilometers in the case of intercontinental delivery systems. So there are a few types of missile technologies that we can speak about. The first is the cruise missile. This is the first variety of the missile that was developed in the 1940s. So these are in most ways analogous to an uncrewed airplane. Instead of a pilot, you have an autonomous guidance system and a propulsion system. Instead of a cargo of passengers or mail or what have you, you have an explosive warhead. Now, in a general sense, these tend to be, compared to other missile technologies, relatively slow, usually used for shorter range delivery missions, but can also be, under certain circumstances, cheaper, easier to produce than our second category of missile technology, the ballistic missile. So this is, in many ways, analogous to a space launch vehicle. So what you see here is actually a repurposed Peacekeeper ICBM, now used as a space launch vehicle. You have a very large rocket engine. So most of what you see here is just fuel and the engine itself. And then at the tip of this, you have a small payload containing reentry vehicle. So what happens here is this thing will burn all of the fuel that it contains in just a few minutes in its boost phase of flight. That engine and those fuel containing components will fall off, drop back to the surface, and then just the warhead containing reentry vehicle will continue solely under the control of gravity all the way to its target when it falls back to Earth. So this variety of missile tends to fly much faster than a cruise missile, can achieve typically longer ranges in usual designs, and is kind of the state of the art in a lot of ways. Now, there's a third missile technology, which is what we're interested in here, the hypersonic missile, a glide system. So this is often considered an emerging technology in the present day and is the focus of a concerted effort to develop these systems as part of an arms race between the US, Russia, and China. A number of other nations are additionally developing hypersonic weapons, but these are kind of the leading military powers. So let's talk about what a hypersonic missile actually is, which gets a bit complicated. So the term hypersonic refers to a velocity regime. And this diagram here splits the velocities of a aerial vehicle, an airplane, a missile, what have you, into three different velocity regimes. So on the left-hand side, you see the subsonic regime. This is things that fly slower than the speed of sound. Another way of saying that is slower than Mach 1. So this is the realm of things like typical commercial airliners. Faster than Mach 1, you have next the supersonic regime, so things that fly faster than the speed of sound. This doesn't fly anymore, but the Concorde, a commercial airliner, did at one time fly passengers in the supersonic regime. So this is a bit more of an extreme regime of velocity, but still something that many people are familiar with. Then finally, on the right-hand side, for Mach 5, or 5 times the speed of sound and above, we have the hypersonic regime. Now, in a conventional narrative, this is the realm of these kind of strange experimental systems. The X-51A, the X-15 are systems the US has developed and tested. The X literally stands for experimental here. But that kind of misses the point because, in fact, the first ballistic missile that was ever designed and used, the German V2, many hundreds of them were launched during the Second World War by Germany at the UK and Belgium, flew just short of this hypersonic velocity cutoff. And modern intercontinental ballistic missiles, the kind that many nations, the US, France, China, Russia, the UK, field, fly well into that hypersonic regime. In excess of 20 times the speed of sound is common. So it's not really the velocity that distinguishes hypersonic weapons, even though in a physics sense, that's what this term hypersonic means. Rather, the distinguishing factor here that we care about is the trajectory, the path that they fly to their targets. So what I show here is a typical trajectory for a ballistic missile. So on the left-hand side of the screen, the image you see there is a North Korean transporter erector launcher, the platform on which a long-range missile is launched from. So when one of those missiles is launched, as I mentioned earlier, these ballistic missiles, the current state of the art, they will burn fuel for just a few minutes in what's called the boost phase. That engine, so most of the missile you see there on the left-hand side of the screen, will detach and fall back to Earth, whereas a smaller re-entry vehicle, this conical nose section that you see on the right side of the screen, will, now that it's been accelerated to very high velocities, hypersonic velocities for an intercontinental mission, will then fly outside the atmosphere under solely the influence of gravity on a ballistic trajectory all the way to its target. For intercontinental range delivery, as shown in this cartoon, this will reach an apogee or a highest altitude on the order of thousands of kilometers and will only spend a few minutes at the start and end of its flight, the boost and terminal phases, traversing the atmosphere. The rest of the time, these will fly through outer space on a typical minimum energy trajectory. This is different for a hypersonic glide vehicle. So what's shown here is that different trajectory. But note on the left-hand side of the screen, the launch platform is essentially identical. And the boost phase actually looks essentially identical. You accelerate these things in essentially the same way you would a more conventional ballistic missile. The difference is shortly after that boost phase, rather than traveling on this high arcing trajectory, you'll then re-enter the atmosphere and glide through the atmosphere for a long period of time, somewhere under 100 kilometers in altitude, so within Earth's atmosphere. For an intercontinental delivery, you might be gliding for something on the order of 20, 25 minutes. So essentially what you're doing is taking the same launch vehicle and replacing that ballistic missile reentry vehicle with a hypersonic glide vehicle, something designed to glide through the atmosphere like an aircraft rather than to fly through outer space on a ballistic trajectory. So the key question of all of this is, does it matter? What does it mean? Why do you want to fly this glide trajectory instead of the ballistic trajectory that is far more common, far more frequently accessed with currently deployed systems? So some potential proposed answers to that question of why I show here. And I want to note these include sources from the mass media, from defense analysts, from government officials. And what they're all saying is sort of wrapped up in this idea of a hypersonic revolution, that these missiles are game changers, that they are faster than any other kind of missile, and thus they reach their targets in a shorter period of time than what any other missile technology can do, that this leaves insufficient time for an adversary to even think about responding to you, and that there's no way to defend against or to intercept these missiles. So, what this narrative is espousing is the idea that there is a revolution in aerial warfare brought about by the advent of the hypersonic missile. And so, with this narrative in mind, we became very interested a few years ago in trying to quantify just what's going on here, to simulate the flight performance of hypersonic glide missiles, compare that to other missile technologies. And initially, what we were thinking when we started this work was just how much better are hypersonic weapons? And what we found, and we'll get to in just a minute, is actually a lot of these narratives they lack a clear technical basis. They're erroneous in many ways. And actually, there are serious disadvantages to hypersonic weapons when compared to other missile technology options. But so the way we approached this was not by just pontificating or speculating, but by trying to quantify, trying to rigorously model and simulate just what's going on when a glide vehicle travels through the atmosphere. So just quickly to go through some of the computational modeling approaches that we went with, we wanted to model the flight of a representative glide vehicle through a realistic atmosphere. So for these calculations, we are simulating flight over a spherical Earth. We're using vehicle parameters that we derive from available flight test data on hypersonic systems. We model them using ab initio equations for flight speed, direction, altitude, and range. And we couple that with a realistic model of Earth's atmosphere called the US Standard Atmosphere 1976. Some of the parameters for that as a function of altitude are shown on the lower right-hand corner. And this model we initially developed, which is some kind of complicated, quite ugly, to be honest, Python code, allows us to calculate flight trajectories, flight speeds, and then directly compare the performance of hypersonic glide systems with those of alternative missile technologies like intercontinental ballistic missiles, and importantly, with the performance of other systems like defensive interceptors that might try to defend against an incoming hypersonic weapon. Now, the math here, 6 equations of motion. I won't go into it in too much detail because the whole point of this is that we're trying to develop web applications to make all of this analysis much easier for a typical person to do. But just to show the full math here, we're essentially integrating 6 equations of motion over time using Runge-Kutta methods to simulate the full trajectory under the influence of gravity, drag, lift, all the forces that a glide vehicle would encounter as it flies through the atmosphere. And now, when we first started doing this analysis, we quickly came to find that many of the common narratives of hypersonic missile performance from those quotes that I showed earlier lack a sound technical basis. They are not serious, rigorously derived understandings of what these weapons do, but are based oftentimes on a kind of mythology or an imaginary of what a fantastical weapon system could achieve, but a real one probably couldn't. So just to quickly show a few of these findings, a key one is that when you glide through the atmosphere, rather than flying through outer space as a ballistic missile for a long-range mission does for most of its trajectory, you suffer from the influence of drag. When flying through the atmosphere, you're flying through fairly dense air, and thus that drag will quickly slow a hypersonic glide vehicle as it continues to fly. So even if it starts at a high speed, it will lose that velocity over time. So in this plot, what I show are 5 different color lines. These correspond to different initial glide velocities. So the initial velocity of the glide of a hypersonic weapon through the atmosphere is really just a function of the size of the rocket booster on which you fire it, on which you accelerate that to high speeds. So maybe you're willing to invest more, launch it on a very large rocket booster, get it up to 7 kilometers per second at the start of glide. Maybe you have a somewhat less expensive, slower system, 5 kilometers per second. I just show here a kind of representative range of initial speeds. But what we see in all cases is that you start at a high glide speed, but as you move from left to right here across the x-axis to greater glide ranges, you see that that speed quickly decreases as you glide through the atmosphere and suffer the effects of drag. If you look at that central brown line, for example, if you start your flight at 6 kilometers per second, by the time you've been gliding for 6,000 kilometers, just for reference, for example, Moscow and Washington, D.C. are about 8,000 kilometers apart. So by the time you've been gliding for 6,000 kilometers here, you'll be traveling about 3 kilometers per second. So your velocity will have been halved by the effect of drag. This matters a lot for things like delivery time, how long it takes your weapon, your missile to carry its payload from point A to point B. So here I have the time it takes to glide a certain distance, again, as a function of glide range. Now, again, those 5 differently colored lines corresponding to initial glide velocities. And then also this gray dotted line, which shows the glide time that you would have in the absence of drag if you were flying through vacuum, if Earth had no atmosphere. And so the gap between the gray line and the colored line shows you the additional time that it takes you to fly a certain distance because of the effects of drag. And what we see here is that that can be pretty substantial. So if you start with something like a 20-minute glide time and then you add 5 minutes, 8 minutes to that, it's a pretty substantial penalty that you're encountering because you chose to field and use a hypersonic glide system rather than something like a ballistic missile that flies primarily through the vacuum of outer space outside of Earth's atmosphere. And now we can compare that directly with the performance of a ballistic missile. So this is showing the results of a simulation where we essentially take the same rocket booster, the Minotaur 4, which is a repurposed version of the US Peacekeeper ICBM boost vehicle, the largest that the US has built and planned to deploy. And in our simulation, we can put an ICBM reentry vehicle, a ballistic missile system on the front of that, or a hypersonic glide vehicle on the front of that and compare for all the same conditions, the same booster, essentially the same system, other than the vehicle and then the post-boost trajectory, how long it takes these things from launch to impact at a target to fly that distance. And what I show here for delivery time as a function of range is that contrary to that common narrative that I discussed earlier, that hypersonic weapons reach their targets faster than any alternative missile technology, actually, for essentially any realistic military mission, hypersonic missiles are slower than their ballistic missile counterparts when you fly the ballistic missile on a depressed trajectory, which is optimized for shortening delivery time. So we see that at lower ranges, this gap narrows a bit, but there's no crossover. There's no point at which actually a hypersonic glide delivery system, when both missile varieties are optimized for delivery time, can reach its target quicker than a ballistic missile can. The hypersonic missile, in terms of delivery time, is actually slower. So this kind of shows why it's important and useful to do this kind of analysis. The last of the results I want to show is another reason that it can be useful to understand these things in a quantitative manner. Uh, so when we talk about utility, prediction of this performance is important for enabling technically informed policy. So I want to show a really specific example of that. Here we're looking, this is the most complicated plot I'll show. So here we're looking at velocity as a function of altitude in the terminal phase of missile flight. And again, we're comparing a hypersonic glide vehicle with a more traditional ballistic missile. And so the right way to read this plot is from top to bottom. We're going from high altitude down to eventually zero altitude when the missile hits its target. And as it's doing this, as it's diving down towards Earth's surface, it slows. So that's why you see those 2 colored lines trending towards the left when you get to lower altitudes, because these things are flying through increasingly dense air as they get to lower and lower altitudes. What we see is that at no point during this terminal phase, given the same boost conditions, so launching these again on the exact same boost phase delivery boost system, At no point does the hypersonic glide vehicle travel faster than the ballistic missile system. And in the terminal phase, this matters a lot because this is when you're most vulnerable to interception in many ways. So if you're thinking about evading defenses, what this tells us is again, in direct contradiction to that conventional narrative, there seem to be some clear advantages to using a more traditional ballistic missile system because in the terminal phase, you're maintaining much higher velocities since you haven't been subject to the effects of drag and the velocity losses that stem from that. You have better capability in many cases to try to maneuver around and dodge incoming interceptors. And so when we started doing this kind of analysis, which we published a paper on in early 2023, one of the things we predicted was that, contrary to this common narrative, actually many hypersonic weapon designs would be pretty vulnerable to this kind of terminal phase missile defense. And it's pretty nice when you make these kind of predictions and then they're validated shortly thereafter in the real world. And we saw exactly that play out in the Russo-Ukrainian war when in mid 2023 and continuing to today, Russia started using hypersonic missile systems, the Kinjal, which is kind of debated whether it should be called hypersonic, but then also the Zircon hypersonic cruise missile, which is clearly a hypersonic system. And the Ukrainians started pretty regularly intercepting these using Patriot missile defenses, which are these exact sort of terminal phase missile defense systems that we were doing analysis on. So again, we see a value of this kind of analysis because it can help us to predict what the security implications are, what the strategic implications are of these kinds of weapons, even when there's a sort of hype narrative going on that might not really align with physical reality. Another benefit of this is that it can help in a more policy-oriented way beyond the strategic and immediate security implications. It can help to just make effective international security policy. So an example here is a 2023 report by the Congressional Budget Office, where after we started publishing some of this work, they were interested in the modeling they were doing. We talked to them, provided some of the computational tools we had developed, and they used those as a basis to do more complex conflict scenarios, modeling of hypothetical conflicts between the US and Russia over an invasion of the Baltics, and the US and China over a conflict in the South China Sea. And they came to some interesting conclusions here. We're using some of these computational tools we had developed. They were able to show in quite a rigorous way that deploying these hypersonic glide systems wouldn't necessarily offer you any appreciable advantages over the deployment of more traditional, more well-developed ballistic missile systems. But being the Congressional Budget Office, they went further than that and actually showed that there was a significant economic disadvantage, a cost disadvantage to the use of hypersonic weapons. They don't get you anything additional in terms of performance or strategic or tactical leverage, but they cost significantly more than the ballistic missile systems you might otherwise develop. So again, a way that this kind of analysis can be quite important for policymaking activities. So all of this is work that we've done in the past. Moving forward, the thing that we've been working on recently, and which we're now debuting with this hypersonic glide vehicle simulator application, is a way of enabling analysis of this in this rigorous quantitative way using these simulation techniques for users without the kind of technical experience required to handle very ugly Python code modeling quite complex aerodynamic scenarios. So what we've developed is what we hoped is a very user-friendly way of doing this exact same modeling using an easy, nice-looking graphical user interface without having to see any of the code that's happening in the background. So the last thing I want to do is show that and walk through a bit what it looks like to use this tool that we've developed, which we call the Hypersonic Glide Vehicle Simulator. So you can access it at this URL here, camerontracy.github.io/tools. You'll see a link to the simulator itself. You'll also see there a user manual, which I really, if you're going to use this tool, I highly recommend you take a look at because it will make the use of it even easier. But what I'm going to do now is just walk through some quick examples of running it. You're free to, if you want to log on to this, if you want to go to this URL, try to follow along. I will caution that if many people are trying to use it simultaneously, it can, there's a lot of computation going on in the background there. So it might not run at this very moment, like while we're doing the webinar, but definitely you can use it in the future at any point in time, and there probably won't be many users at that point. So what I'm going to do is I'm going to stop sharing here. I'm going to bring up my browser and show you exactly what it looks like to use this computational tool. And you'll see the URL for the web app there as well. So don't worry if you don't have this one copied down. Okay, so here you see the glide vehicle simulator itself. Here's the longer URL for it up here. And it's a pretty simple user interface that we show here. So all it is a few parameters that are necessary for modeling the entire hypersonic glide flight trajectory, which is the initial flight conditions that you would have. So most importantly, the velocity of your system, the speed to which it is accelerated at the start of the glide phase, and then a few angles for the exact orientation of that initial flight direction in 3 dimensions. And then what's really nice is that you can model essentially the entirety of the with just the ballistic coefficient, which is essentially a ratio of mass to drag, and then a second LD, or the lift to drag ratio. And now I want to talk here in that user manual. Sorry about that, everyone. I think the Zoom died for a second, but let me just get right back to where I was. Okay, so hopefully you're all still following along and can see right back where I was. So all I would do is enter all of these parameters on the right-hand side of the screen, click Run Simulate at the bottom. Just to reduce the computational load, I'm not going to run one now. I did earlier. So once I click Run, well, I'll show you what happens actually. It'll tell me with this helpful little pop-up that it's running the simulation, and in a few minutes, it'll show me the results. And so just with those default conditions here, this is what you'll end up with if I run that simulation. It'll output a bunch of useful summary statistics, how far the thing flies, how long it takes to fly that distance. Then you can see some plots. So the altitude that it flies versus range. You see here some small bounces. This is called a phugoid trajectory. It's very nice that our model reproduces this because it's what you actually see when you fly one of these systems through the atmosphere as they bounce slightly between lower altitude, denser air and higher altitude, more rarefied air. See, velocity is a function of range, again, reproducing that drag effect that I talked about earlier. Flight time is a key parameter that you might be interested in for understanding the delivery time penalty resulting from drag. Here, cross range, so if you're turning to the left or right. So up here at the top, I didn't enter a roll angle, which is how these systems turn. I'll show you what that looks like in a moment. So here you can see the y-axis. This is in micrometers, so it's essentially zero. Those are computational artifacts. It does an interesting thing called footprint analysis. So we can simulate this vehicle turning to the left or right. One of the advantages of a glide vehicle is that you can maneuver throughout flight. And this shows you the full area over which a system could maneuver to if you were interested in turning to the left or right to strike a different target. Once we have that, we can also project it onto a map. So what we see here, by default, it always starts where I am right now, and Justin is as well in the San Francisco Bay Area, and then shows if a missile starts gliding here, this is the entire footprint, the region of Earth that it could strike. And in the center, that solid red line, you see the straight trajectory if it weren't turning. So that's the maximum downrange it could achieve. You'll see this is going to be important. The red line curves. This is a projection of a spherical globe onto two dimensions, so straight lines look distorted. That's actually the red one is a straight line across a spherical globe. And then at the bottom, you'll see also the tabular data. So we do every 5 seconds a calculation of the trajectory. So you can output this data to an Excel format file if you want to do real analysis yourself, rigorous analysis of numerically what's going on in this code. So what we're trying to do here is just make all of this quite easy. So you can really simply get this trajectory, this projection of exactly what's going on. So an example of how you might use this. One application would be to look at this kind of intercontinental range missile attacks oftentimes are planned for use against an adversary's nuclear forces. This is what's called a counterforce attack. And the idea is that not targeting people, not targeting San Francisco, New York, Washington, D.C., is a more ethical way to approach war, nuclear deterrence, and so on. So counterforce rather than what's called countervalue targeting cities. Now, oftentimes with a ballistic missile system, for example, it would be relatively easy to distinguish a counterforce from a countervalue attack, since ballistic missiles mostly fly straight lines over the Earth. But with a hypersonic system, that's not so true. So this is one risk that might be introduced by the use of a hypersonic vehicle, difficulty with distinguishing from counterforce and countervalue attacks. With this tool, you can quantify just what that risk looks like. So here I have a tab where I entered some parameters that represent what a Russian hypersonic vehicle use scenario might look like. Now, Russia currently deploys a hypersonic glide system called the Avangard on their SS-19 boost vehicles. So based on characteristics of the SS-19, this is an example again that we walk through in the user manual. You can estimate an initial glide speed of about 6 kilometers per second. So I enter that here. And looking at similar hypersonic systems that the US has flight tested, we can estimate probably reasonable ballistic coefficient and lift to drag conditions. And then if we select this calculate threatened footprint option, then we run the calculation, and what we'll output is this map projection. And if we enter the right coordinates here, this shows where a missile would re-enter the atmosphere and start gliding if it followed a straight line from where Russia deploys their SS-19s armed with the Avangard boost glide system and were to launch it directly towards US ICBM fields, so US nuclear weapons, this is towards the Minot Air Force Base in North Dakota. So that's where the red line is going. But what we see here is the maneuvering capability. So something that is flying towards US ICBM fields could potentially turn. It could maneuver, turn left or right. And what we see is that it could threaten essentially the entire continental United States, not to say essentially all of Canada and Mexico as well. So this creates a risky situation where in a hypothetical Russian strike on American ICBM fields, this couldn't be easily distinguished in the early stages of flight from an attack on San Francisco, New York, Washington, D.C. So this is a way we can quantify some of those risks associated with what we could call target or destination ambiguity associated with hypersonic weapon use. So one last example I'll show. In addition to looking at this footprint, we can look at maneuvering for more tailored missions. So one reason certain states are interested in hypersonic weapons is for the potential to avoid overflight when you're conducting a missile strike of a region you don't want to fly your missile over. So one way in which this might be important is if we look at a US missile attack on China. So here I'm just entering an extremely high velocity to look at where a missile would fly if it were going from the United States to China. And if I run this simulation, I get this. So again, this is simulating straight flight. So it looks like a curved line. That's just because it's a projection of a sphere onto two dimensions. A straight line from the United States towards China flies over other countries, Russia, for example. So if the US were interested in targeting China for a military strike, it's probably not a good idea to fly over Russia, a nuclear armed country, because they're going to start thinking, hey, this looks like an attack on us. And so that might invite inadvertent reprisal. For other trajectories, towards other parts of China, you might instead fly over countries like North Korea, also nuclear armed, a US ally like Japan. So you might be interested in using hypersonic weapons to avoid that with the idea that they could fly around these other countries and then maneuver towards China. So you're really only overflying the Pacific Ocean. That's something that we can directly quantify. So here's a calculation we might run. This is for a hypothetical launch of a US hypersonic glide vehicle from Malmstrom Air Force Base in Montana, launched on the front of a Minotaur 4 boost system. So again, in the user manual, we walk through this, but a reasonable estimation for an initial velocity of this kind of glide vehicle is about 6.1 kilometers per second. And again, we're interested in using this turning capability. So I'm going to start with a roll angle, which is how a vehicle turns of 60 degrees. And then I'm going to simulate a system that the US has currently deployed, the Common Hypersonic Glide Body, which is a kind of lower performance system than what the US has tested in the past. So a reasonable estimate of a lift to drag ratio here is 2.2. Now, if I run this calculation and additionally tell it here using this complex maneuver capabilities to turn for a certain period of time, but then once you're flying at the trajectory you want straight towards China, to switch your roll angle back to 0 and switch back to straight flight. What we're going to come out with once we run our simulation is this. So this is again from Malmstrom Air Force Base in the US, a ballistic system flying a straight line, then re-entering the atmosphere about 1,000 kilometers off the coast of Japan and trying to turn towards China. And the idea here is that what I'm trying to fly towards in this case is a Chinese military installation called Brigade 616, where they deploy some of their intercontinental range missiles, which is located in Guangzhou, China. And so here we've entered this maneuvering trajectory where we turn for a certain period of time, and then once we have the heading we want, we switch back to straight flight. And what we see here is that we're flying towards this military installation in Guangzhou, China, but we don't quite make it. So this velocity or this lift to drag ratio, the aerodynamic parameters of our system, seems to be insufficient for carrying out this mission. It doesn't have the maneuverability it needs. It gets slowed by drag before it can reach its target and will fall to Earth short of that target. But what we can do then is really look at what kind of performance parameters our missile would need. So if we're thinking about future missile technology developments to carry out this mission. So here I can run the same calculation, all of the same parameters, but I'm using a slightly higher lift to drag ratio. So a hypothetical higher performance system. And we can see exactly the aerodynamic parameters that we would need to here execute that same trajectory, that same turning motion. And we see with these better performance parameters, we now can reach Guangzhou and we have a little bit of excess range as well. So this is just an example of some of the analysis you can do with this tool. Again, if you want to access it, here's the URL you can use. There's a handy user manual, which if you're going to use this tool, I would highly recommend you take a look at. So I'm going to stop here and then switch over to my colleagues, Justin Lee and David Wright. And I'm going to pose a couple questions to them about the development of this tool and why it's important to have this kind of analytical capability. So I'm going to start with Justin, who is a computer science student, a graduate student, and did really a lot of the graphical user interface, the development of this app to make it easy for users to access and to make use of. So Justin, I wonder if first you could just quickly walk us through some of the considerations that went through your head, what you were thinking of when you were designing something to take pretty ugly technical code and make it something that a user might actually derive some value from, even without a technical background.
Yeah. So the biggest goal was accessibility, and simulating something like a hypersonic glide vehicle is normally the domain of people with very specialized tools and training. So I wanted someone without that background, maybe like an analyst, a student, or a policy researcher to be able to sit down, set a few parameters, and get meaningful results without needing to understand the physics engine running underneath this app. And so a big part of that was minimizing what the user actually has to think about. So you're setting maybe about 7 inputs and then hitting one button and you get everything at once, the flight path, the heating, detection signatures, all that threatened area. And behind the scenes, there's a lot going on, like the validated atmospheric models, the heating equations, but the user doesn't need to touch any of that, and it runs with solid defaults that the app comes with. And if you're an advanced user and you want to dig into those details, you can expand those options, but they're tucked away by default so they don't overwhelm a user that may not know what to do with the app the first time they're using it. And then the other big goal was serving different audiences with the same tool. So say an engineer wants to download the raw data, there's the spreadsheet at the bottom of the app that they can do their own analysis with. But maybe someone preparing a briefing or a policy memo may want a chart or a map that they can drop into a slide deck. And so the app gives you both from a single run, um, and a geographic map showing where the flight path and threatened areas fall in the real world. And so the idea isn't that, or the idea is you shouldn't have to run the simulation twice to get the version of the output that's useful to you.
Yeah, thanks. One thing that I really like, which you did great work on here, and was your idea, was to do this map projection. So when you're really doing the analysis yourself and you're steeped in it, oftentimes you know, like in your head, what it means to be able to turn left or right by, say, 1,000 kilometers cross range. But if you're not really steeped in that, if you're not thinking about it every day, you really need to be able to see it on a map, right? To understand, well, this means it could turn left and hit New York instead of ICBM fields in Wyoming. So I really like that aspect of the tool that you designed into it. David, so you have a long career, you've had a long career and continue to doing this kind of technical analysis, this physical engineering analysis of military technologies, but doing so for the purpose of informing policymakers, informing those in the strategic studies and security studies communities, and helping them to understand just what the implications of these kinds of technologies will be. Can you talk a little bit about why that kind of work, that interdisciplinary interaction, is so important, both historically and today, as we move into a new era of, missile defense expansion, the use of new missile technologies in ongoing real-world conflicts?
hmm I got into this business back in the 1980s in part because I saw that there were security issues, policy issues that had important technical aspects to them. And it was clear that there was a need for scientists and engineers who outside of the government who could look at these issues, make sense of them, and provide information to a variety of different audiences. One of those is policymakers. Policymakers often are busy with a lot of different things. They may not have staff who have the technical ability to understand some of these issues. And so making some of this information available to them is I think, surprisingly useful sometimes. The other thing is, reporters and the public to try and understand what people need to know, especially reporters who are interested in trying to dig into some of these issues and get them out to a broader audience, or even for people in the public who want to understand these things better to be part of the public debate. I've always seen this kind of work as an important part of enhancing democracy because I think it gives more people the ability to understand and weigh in on some of these issues. And that's particularly important in an issue like security, where there's a lot of classification. And so a lot of times information is not readily available for people. But what we found time and again is that as a scientist or an engineer, by understanding some of the basic principles, you can't classify that basic science or engineering, and it allows you to understand enough to really uh, understand some of the key issues. And I think the hypersonic work is a really good example of that. I mean, by understanding aerodynamics and things like that, we were able to make a lot of progress on understanding some of this. And I think the last point I would make about this is that there's a surprisingly small community of scientists and engineers outside of the government who do this kind of work. And I really appreciate the fact that, for example, the Berkeley lab is hiring people like you to do this kind of thing. The Union of Concerned Scientists, where I worked for many years, was supporting people to do that. And again, I think that's a really important part of helping people take part in these important debates.
Yeah, thanks. It's really interesting the extent to which this kind of analysis and these issues are oftentimes just closed off to not just the public, but even to people interested in security issues. I get the question all the time, when I'm describing the kind of work that I do. Well, isn't that classified? How can you say anything intelligible about that? And exactly the point you made is how I always respond, which is you can't classify physics, right? This is one of the benefits of science is that it doesn't necessarily always work this way, but it has this great democratizing potential of making knowledge and knowledge generation accessible to huge swaths of the population. Oftentimes, though, there is that barrier to entry. Like it's hard to learn and to do physics, right? And so that's exactly what we're targeting here, trying to make that kind of physically rigorous work accessible to broader swaths of the interested community.
Mhm.
So thanks so much. Really, really insightful comments from both of you. There's a lot more I'd like to ask you, but I do want to give a chance for the audience to ask any questions they might have as well. So if there are any questions, Vivian, I believe they would put it in the chat. Is that correct? Yeah, so if you can put any questions you might have in the chat, I'd be happy to read those to our panelists and respond to any questions you might have about how you might use this tool, or even comments, ideas anyone in the audience might have for improving the way that it works. But in the meantime, I want to pose one other question to David. So in addition to the kind of work that we've been doing on the simulation of hypersonic glide systems, you've been doing a lot of work on missile defense, which is becoming increasingly important. We're seeing the use of defensive systems in the ongoing war in Iran. We've seen them play key roles in the ongoing Russia-Ukrainian war. Can you talk a little bit, and also, of course, I need to mention Golden Dome, the U.S. planning to make vast investments into missile defense. David, can you talk a bit about where we are with missile defense deployment in terms of any gaps that might exist, as we've talked about in the hypersonic missile case, between what people expect these systems to do and what they actually might be able to achieve, and how we can better understand or explain and communicate as technical practitioners what we should expect these systems to do and their security implications.
Mhm. One of the reasons I think the missile defense debate comes back again and again over the years is that it's such an appealing idea. I mean, once you have ballistic missiles that can threaten you, the idea of trying to come up with a system that could defend against them is obviously something that you'd like to have, and the politicians very much would like to be able to have in their back pocket. And so part of what we see is that time and again, people think that if you spend enough money or have a good enough technology that you can beat this system. You can build a system that works. And in fact, what I've found in the years I've been working on missile defense issues for 40 years now, and what you find is that it's not a purely technical issue. In particular, one of the things that keeps coming back is if I'm trying to hit an incoming warhead with my interceptor, it's not just hitting a bullet with a bullet. People always say it's like hitting a bullet with a bullet. Turns out that's a technically well-defined problem that you can do, and we've done it any number of times. The problem is that it is in the attacker's interest to make it very hard for the defense to identify the bullet, or to have a lot of fake bullets so that the attacker doesn't see, a warhead coming down, but sees what appears to be 20 to 30 objects coming down, any one of which could be warheads. And then the problem is, even if you have a system that could attack them, you don't know which is the right object to attack. And so I think that's a good example of the kind of things that, again, take some technical understanding to isolate that as being one of the key problems, but it's not sort of the key well-defined engineering problem that people often think of with missile defense. And I think that's part of the reason that this comes back again and again. As I said, it's a very appealing idea, and if you're not steeped in the details of it, it sounds like it should be doable, especially against, a country like North Korea.
Yeah, thanks. And I just want to plug, you and Steve Fetter had an excellent article in the Washington Quarterly that came out just a few months ago about the lessons that should be learned from recent performance of missile defense systems in Israel, defending against Iranian incoming missile attacks, which is an excellent analysis of some of these issues. We have a question from Lindsay Rand. This is in the Q&A. Sorry, earlier I said in the chat, you can put your questions in the Q&A function. Lindsay asks about the variables that are most sensitive when it comes to the classified specifications that we're looking at in our model, or what variables that the classified community sometimes indicates shouldn't really be known or open to analysis. So I'll kick this over to David in just a second, because David, I think you're really the expert on this kind of open source analysis. One thing we typically look at is missile test flights, if we want to extract from those understandings of the aerodynamic parameters of these systems, like the lift to drag ratio. So just one example of how you can do that. When the US conducts missile flight tests, they're typically launching over the ocean, and they have to put out notices to mariners to stay out of certain areas where portions of the missile, the boost system, when it detaches and falls back down to Earth, where that will be falling into the ocean. And so you can get this pretty nuanced, pretty granular understanding of the trajectories that components of this missile are flying during these test runs, and then can back calculate out from that the aerodynamic parameters and the boost parameters that they must have. And you can get pretty informed understandings of some of the aerodynamics of these systems. But like I said, I'll kick to you, David, for any other comments you have on how the methods that you can use to try and tease out these harder to understand classified performance parameters of such systems.
Yeah, I mean, each system it takes a little sleuthing on its own to figure out what makes sense to what kind of estimates you can do. The thing that I found very interesting about the hypersonic weapons was that there's only one parameter that really matters for a lot of it, which is the lift to drag ratio. Turns out that the ballistic coefficient, for reasons we could talk about, it's much less sensitive to the value of the ballistic coefficient. And even though these things go very fast, they're basically gliders, and people have understood gliders for a long time. And so what that meant was exactly what you're saying, is by looking at the kind of ranges people were able to get in some of the tests of early systems, and the expected ranges as a function of the initial velocity, you can start to get a very good idea of what the lift to drag ratio would be. And with that, you can really do a lot of the other kinds of estimates. And once you get, that, then clearly the thing you do is you say, okay, I'm going to take a value, and then I'm going to do some variations around it and see how much it matters if I don't have exactly the right value. And so often what you can do is make a plausibility case for a value and argue that it's not that sensitive.
Yeah, and one of the things I really like about this tool, in addition to that, is that you actually can do useful analysis without knowing much about the system. If you didn't have, for example, or if you're interested in something that's never been tested, if you're interested in, say, potential future developments far into the future, there might be far more aerodynamic systems, for example, if materials that can better withstand the kind of heating that you encounter during hypersonic glide, and thus you can build systems that are very slender and have sharp leading edges and so on, and you want to understand what that means for the security implications of these systems, you can model that, right? Like you can enter very high lift to drag ratios. Not to say that that will ever be achieved, but if you're interested in understanding what it would mean for international security, then you can model that in a scientifically rigorous way. This is just as valid in terms of the physics as entering more realistic values, if that's the kind of speculative analysis you want to do. And that can be useful. So again, this idea of democratizing, we study technological development in the missile space and try to develop reasonable expectations of what might be achieved in the future. But people can disagree on that, and it can be useful to study in a more speculative manner as well. And that's the kind of capability that we're trying to make accessible to more people. We are just a minute over. If there are any last questions, feel free, please enter them in the Q&A as quickly as possible. But otherwise, unless something shows up in the next second or two, I just really want to thank Justin and David for joining us. Justin Lee is a current computer science grad student, so keep an eye out for future work coming from him because he's done such great analysis here, and I think we'll continue to develop very useful software. And David Wright, as I mentioned, please check out that article that he had in the Washington Quarterly with Steve Fetter on lessons learned from missile defense performance in recent conflicts when used and deployed by Israel and the United States, and probably some upcoming work as well, looking in more detail at simulating, calculating, modeling the performance of missile defense systems, especially as we move into a new era of the Golden Dome initiative, and the US makes vast investments into missile defense systems that, as we heard earlier, we should be a bit skeptical of when it comes to the performance and the implications that they might actually have for the ability of the US to defend against incoming missile strikes from adversaries. But with that, please check out the tool. Again, if you just Google Hypersonic Glide Vehicle Simulator, you'll probably find it. We really hope this is useful to people. If you have suggestions for other things that would be useful to you, new functionality, for example, please send that along to me. I'd be really interested to hear it. And the idea is that this is something that we could evolve over time. And we're also actively developing other such tools to, again, try and democratize, make accessible to larger audiences this sort of technical analysis, make it a bit less technically demanding when it comes to users, while still as technically rigorous as possible. So again, thank you all for attending. Please, become a part of this community. If you're not already, reach out to us. Let us know what we can do to make this sort of analysis more useful to you. And we hope you'll join us for future webinars for new software tools that we develop in the future. Thanks again.